Today I want to go over a classic problem in the calculation of entropy. This is called the coffee and cream problem. I suppose some other people might call it the tea and cream problem, or whatever you happen to be mixing together. The problem is, suppose we pour 25 mils of cream at 5 degrees C into 200 mils of coffee at 70 degrees C. What will be the final temperature? Well, that's not hard. How much is the entropy change of the coffee? How much is the entropy change of the cream? And how much is the entropy change of the universe? The first thing we need to do is state the assumptions that we'll be using. The heat capacity for both the coffee and the cream will be given as the same as that of water. 4.176 joules per gram K is what I'm going to use. The density for both coffee and cream will also be taken as 1.0. So that means that volume is going to be equal to mass. And thirdly, the addition of the cream to the coffee will be so quick as to be able to assume adiabatic conditions, that is, the change in heat will be zero. All right, the first task is to calculate the final temperature, and we are going to use delta Q is mass times Cp times delta T. And this is cumulative, so since we know delta Q is 0, that's our adiabatic condition, we can say the mass of the coffee times its heat capacity times the final temperature minus the coffee temperature, that's the delta T. And then we can do the same thing for the cream, the mass of the cream times the heat capacity times the final temperature minus the temperature of the cream. Furthermore, because Cp is common to both of them, we're going to be able to cancel that out. All right, so if I multiply this out and expand to the parentheses, I'll simply have the mass of the coffee that times the T final minus the mass of the coffee times the initial coffee temperature, mass of the cream times the final temperature minus the mass of the cream times the initial temperature of the cream, all equal to 0. And then I can go through here and factor the temperature final out, getting me the temperature final times the mass of the coffee plus the mass of the cream, and move the two negative terms to the other side. Then I can divide by the mass of coffee and cream, giving me the final temperature. So let's plug some numbers in. Then we'll see what our final temperature is going to be. 200 grams times the 70 degree temperature of the problem. And that has to be expressed in Kelvin, so I add 273 to it. And then 25 grams times the 5 degree temperature of the cream, and I have to add that 273. And then that's going to be over the mass of the two, mass of the coffee and cream, which will be 200 plus 25. That's going to give us a final temperature of 335.93, and of course that's in degrees Kelvin, which is what we're going to need. So that takes care of the first question that was asked. What will be the final temperature? We have got that one. Now they want to know how much is the entropy change of the coffee, how much is the entropy change of the cream, and finally how much is the entropy change of the universe. Well, the first thing we need to do is find ourselves an expression for entropy to calculate with. So what I've done, I've written down here the first law in terms of enthalpy. You might know this as dH equals change in heat minus VDP, just as I've written it, or you might actually know it as dH is equal to T delta S minus VDP. I'm going to get to that awfully quick. Let's write a few other things here that we know. We know that for this particular problem, we're in a coffee cup. The change in pressure is essentially 0, i.e. there's no change in pressure. We also know that dH is in Cp dt, and this is one of the expressions that we've asked you to memorize for the purpose of thermodynamics. And then finally, we know that dq is T delta S. Indeed, you were thinking about using T delta S up here in the first place, where S is entropy. So, that being the case, let's move on. What I want to do is I want to plug expressions into the first law. So I'm going to take this one, N is moles, but we're going to use as mass because our Cp is mass. So we have mass times Cp times dt. That takes care of the delta H part. And then the dq will be replaced with T delta S. And the dP, well, we've already said the dP is 0, so I think we'll just omit that. Then we can do a little bit of algebra on this, and we'll get ds is equal to the mass times Cp times dt over t. And we're going to integrate both sides of that. Now, the integral of ds is big delta S, and mass and Cp we're assuming are constant. So then we're going to have an integral from t initial to t final of 1 over t dt. And that's going to give us delta S is mass times Cp times the log of t final over t init. That will be the equation that we'll calculate with. So the only thing left is to plug in values to calculate. And we're going to start out with the coffee. So delta S will be 200 grams times the heat capacity, 4.18, times the log of the final temperature, and that's the temperature we calculated earlier, over the initial temperature. There's the 70 degrees, and of course we're trying to do this in Kelvin. When you multiply that out, we're going to get minus 17.78 joules per Kelvin. So the entropy went down in the coffee. Now let's look at the cream. For the cream, we have a delta, we have 25 grams, the same heat capacity, the same final temperature, but then the initial temperature was 5, and so that's a much greater difference. And it turns out, even though we've got much less volume, we're going to get a slightly greater delta S in joules per K, so that's going to go up. And finally, we need the total, and the total is nothing more than the sum, so the delta S of the universe is going to be minus 17.78 plus 19.72, or 1.95 joules per Kelvin. Okay, the last thing I want to do is show you an applet for this problem, and I'll leave a link in the notes so that you can find it. But here we have a cup of coffee, and our initial coffee temperature we've set at 70, and our coffee volume we've set at 200. Now, the way this applet works, we could actually set anything we wanted. We could have put 201 if we wanted, but we don't. We want 200 for this particular one. And then our initial cream temperature was 5, and we have 25 mils of it. So the equations that we use have been put in up here for the coffee, for the cream. The temperature is going to show up right here as we calculate. And then this is the delta S of the universe, or the overall delta S. So I'll start, and you can see that what's happening, let me just stop it for a second. You can see that what's happening is the cream is being put in, and as it does, the coffee cools, and we've gotten from 70 all the way down to 67. We've put in only 7.75 mils of cream at the time that I stopped it, and our delta S of coffee at the time that I stopped it was negative. But notice that the delta S of the cream is ever so slightly greater, and it's always ever so slightly greater, because the combined is the entropy of the universe, and there's a rule, I think it's called the second law of thermodynamics, which is that the entropy of the universe will always be 0 or positive. It'll never actually be negative. All right, so let's just continue this on, and we're putting in all the rest of the cream until we get up to 25 grams. There, we got it. We've added 25 grams of cream. And our final temperature is 62.78. Of course, that's in degrees C. Something the widget does for us is to subtract. I think we had 335 point something before. And so this subtracts off 273 and shows it to us. And it shows us our delta S overall as 1.94 joules per K. So anyway, that's all I have to show you. This solves the coffee and cream problem. And I hope you enjoyed the video. Thank you.